Welcome back to the deep dive. You know how we do it. We tackle some dense source material, really get into it, and pull out the core knowledge you need. Today we're looking at something fundamental, almost primal in physics, vibrations and waves.
Yeah, we've got a great set of physics directives here. And our goal is, well, to trace that line from the simplest back and forth motion, think a pendulum, all the way to some pretty extreme stuff like sonic booms. We're essentially breaking down what's moving, how's it moving, and what happens when these movements interact.
Right, and that story really has to start with the basics of oscillation. Any vibration at its heart is just a movement back and forth around some kind of equilibrium point. And you mentioned pendulums. We have to talk about Galileo. Galilei, his observations were, well, foundational.
They really were. What he figured out, which is kind of amazing, is that for small swings, the time it takes for one complete oscillation, the period, it's incredibly regular. It doesn't really depend on how heavy the weight is on the end. And importantly, it doesn't depend on how far back you pull it, within limits. It's mostly about the length of that string or rod.
And that consistency, that predictable period, is why it became so important for timekeeping. And later, proof of something much bigger, you think about the Foucault pendulum in 1848.
Right.
It used that super consistent periodic motion to show really elegantly that the Earth is actually rotating underneath it.
Exactly. It's like a cosmic clock proving planetary motion, all stemming from understanding that simple vibration.
So that fundamental back and forth, that's
Yeah.
the vibration, the tetritium.
Yes. And when that vibration happens over and over, providing continuous energy, that's what generates what we call a wave.
Okay, so vibration is the engine. Let's look at the vehicle, the wave itself, the anatomy of a wave, dalga. When that continuous vibration creates a disturbance that travels, say, through space or a medium, we often draw it as that classic up and down shape, the sine curve.
Right. And that sine curve, seems easy, it visually captures the key features. First, you've got amplitude. That's simply how high the wave gets from its resting point, the maximum displacement. Then there's wavelength, dalga boyu, usually shown with the Greek letter lambda. That's the distance from one point on the wave to the next identical point. So like from one crest, tepe, to the next crest, or one trough, sucor, to the next trough.
Makes sense. Then we need to talk about time. How fast is it oscillating? That's frequency, frekans, labeled $5. It's the number of full cycles that pass a point every second. And we measure that in hertz. And the flip side of that is the period, or $2. That's just the time it takes for one single complete wave cycle to happen.
And they're directly related, which is key. Frequency is just 1 divided by the period. So 5 hours equals none $t. It's an inverse relationship. If something happens, say, 10 times a second, its frequency is 10 hertz, and its period, the time for one cycle, is 1/10 of a second. Simple as that.
And this isn't just theoretical. Heinrich Hertz, who the unit is named after, actually confirmed radio waves existed back in 1886. He connected this wave physics directly to sending signals to telecommunications. Our sources even point out, AM radio operates in kilohertz, thousands of cycles per second. FM is way up in the megahertz millions. Tuning your radio is literally matching your receiver to that specific frequency.
Okay, so we know what a wave looks like dimensionally. But how does it move energy? This next point, dalga haraketi, is actually crucial and sometimes trips people up. Waves transport energy from point A to point B, but the actual stuff the wave is traveling through, the medium's particles, they don't travel along with the wave.
Right. Think about a cork bobbing on water as a wave passes. The cork goes up, down, maybe a little back and forth, but it doesn't get carried across the pond by the wave itself. The water molecules are doing the same thing, oscillating around their spots, passing the energy along, but mostly staying put.
Exactly. The energy transfer happens because the particles are connected. They push or pull on their neighbors. Think elasticity or tension in a string. It's a chain reaction of movement passing energy, not the particles themselves traveling large distances.
Even something huge like a tsunami. It's an immense amount of energy moving, creating massive vertical displacement. But it's not like the same water molecules are traveling thousands of miles horizontally across the ocean.
That's a really important distinction. Energy transport, not mass transport.
Okay, so knowing that, there are different ways particles can oscillate relative to the energy's direction. This gives us two main types of waves.
First up, transverse waves in 9 dalgalar. In these, the particles of the medium vibrate perpendicular, so at a right angle, deep to the direction the wave energy is traveling. Think about shaking a rope up and down. The wave travels along the rope, but the rope itself moves vertically. Light waves, radio waves, these are transverse.
And the second type?
That would be longitudinal waves, boyu dalgaları. Here, the particle vibration is parallel, it's in the same direction, iniyonde, as the waves travel. These waves work by squishing particles together, that's compression, sıkışma, and then spreading them apart, rarefaction, serikleşme.
And the classic example here is sound, right?
Exactly. Sound waves compress and rarefy the air or water or whatever they're traveling through. And because they rely on these particle interactions, these collisions, they absolutely need a medium. Sound can't travel in a vacuum. There's nothing to compress.
And this distinction isn't just academic. It has huge real-world implications, like in geology with earthquakes.
Oh, definitely. Earthquakes generate both types. Key waves, the primary waves, are longitudinal. They push and pull the rock. S waves, the secondary waves, are transverse. They shake the rock side to side.
And the behavior of those waves tells us so much.
It really does. P waves travel faster than S waves.
Yeah.
And crucially, S waves, being transverse, can't travel through liquids. Liquids don't resist that sideways shearing motion. P waves can. So the fact that S waves don't go through the Earth's outer core tells us it must be liquid. And because P waves arrive first at seismic stations, the time difference between P and S wave arrival tells you how far away the earthquake's epicenter was.
That's amazing. From simple wave types to figuring out the Earth's core structure.
Yeah.
Okay, let's shift gears slightly. Section 3, wave speed and interactions. How fast do they go and what happens when they meet? Dalgaları ve girişimi.
Well, the speed is actually pretty straightforward if you know the wave's anatomy. There's a fundamental relationship, the universal wave equation. Wave speed, dalga sürati, which we call $5, is simply the wavelength, lambda, multiplied by the frequency, $5. So $5 lambda 5rs1. That holds true for pretty much all the waves we're talking about.
And we have a neat example in the source material. Say you have a wave, its wavelength lambda is 1.5 meters, and its period, 2 hertz, is half a second, 0.5 seconds. First you find the frequency, $5 and 2 towns, so $5 1.55, which is 2 hertz, 2 cycles per second.
Right.
Then use the equation, speed $1 lambda set at 5. So $5 1.5 text meters times 2 text hertz. That gives you a speed of 3 meters per second.
See, the math works out nicely. It connects the spatial dimension wavelength with the time dimension frequency to give you the speed.
Okay, so that's one wave. But waves often, run into each other. What happens then? That's interference, right? Dalga girişimi.
Exactly. It's called superposition. When two waves occupy the same space at the same time, their displacements simply add up at each point.
And this can lead to two main outcomes. If, say, the crest of one wave meets the crest of another, they add together. That's constructive interference, displacement.
Yeah.
You get a bigger wave, a larger amplitude.
Correct. But if the crest of one wave meets the trough of another, they work against each other. That's destructive interference, Sanderme. The amplitudes subtract. You might get a smaller wave, or if they're perfectly matched, they could even cancel each other out completely at that point.
That's the principle behind noise-canceling headphones, isn't it?
Precisely. The headphones generate a sound wave that's the exact opposite, the antiphase of the incoming noise. They interfere destructively, canceling out the noise you hear.
Clever.
Now, if you have waves interfering in a very specific, stable way, usually an incoming wave interfering with its own reflection, and they have the same frequency, you can get what's called a standing wave, kararlı dalga.
Ah, yeah, those look weirdly stationary.
They do. They don't look like they're traveling. They're a stable interference pattern. You get points that seem to not move at all. Those are called nodes. Duum. That's where destructive interference is maximal and constant. And then you have points where the oscillation is largest. Those are the antinodes, kadum. That's where constructive interference is maximal. Think of a guitar string vibrating. You see those fixed points and points of maximum blur.
Got it. Nodes and antinodes. Okay, final section. Let's talk about what happens when things are moving relative to each other. The Doppler effect and shock waves.
Right, the impact of motion. Let's start with the Doppler effect, Doppler at Kiesi, named after Christian Doppler, who described it back in 1842.
This is the one everyone knows from like the ambulance siren, right?
Yeah.
Sounds higher pitched coming towards you, lower going away.
That's the classic example. And it's all about the apparent change in frequency because of relative motion. When the ambulance is approaching, it's kind of catching up to the sound waves it's emitting in front of it. So from your perspective as the observer, those wave crests arrive more frequently. Higher frequency means higher pitch.
And when it's moving away.
The opposite happens. It's moving away from the waves it emits behind it, so those waves get stretched out from your perspective. The crests arrive less frequently, Lower frequency, lower pitch.
The actual siren frequency isn't changing, just how we perceive it because of the motion.
Correct. And this isn't just for sound, it works for light, too, which is hugely important in astronomy.
Ah, redshift and blue shift.
Exactly. When we look at distant galaxies, most of them are moving away from us due to the expansion of the universe. The light waves they emit get stretched out, shifting them towards the red end of the spectrum, that's redshift.
And if something were moving towards us, its light would be compressed, shifted towards the blue end, blue shift. It's fundamental for measuring cosmic speeds and distances.
So that covers how motion affects the perception of a wave. But what if the source itself moves faster than the waves it creates?
Okay, yeah, like a boat on water sometimes. See that V-shaped wake behind it?
That's a perfect analogy. That's a bow wave, boru dalgasu. The boat is moving faster than the water waves can spread out ahead of it, so the waves pile up along that V-shaped front.
So what's the equivalent in air for sound?
That leads us to shock waves, dalgaları. This happens when an object, like a supersonic jet, flies faster than the speed of sound in that air. Remember, sound travels as pressure waves. If the jet is faster than sound, the air molecules literally can't get out of the way fast enough. The pressure waves the jet creates can't propagate ahead of it. Instead, they all pile up, compress intensely, and form a very sharp high-pressure boundary. It's typically a cone shape trailing behind the aircraft, often called the Mach cone.
And that cone is what causes the sonic boom.
Yes. The sonic boom, sonic patlama, is the sound we hear on the ground when that sharp edge of the high-pressure cone sweeps past us.
It's important to realize it's not a one-time bang that happens just when the plane breaks the sound barrier. It's a continuous phenomenon. Anyone under the path of that cone as the supersonic jet flies over will hear the boom as the shock wave passes them. It sounds like a sudden explosion because the pressure changes so rapidly.
So there you have it. We've gone from, the gentle, predictable swing of a pendulum.
All the way to the intense energy concentration of a shock wave from a supersonic jet.
And the amazing thing is, it's all governed by the same underlying principles. Periodic motion, frequency, wavelength, energy transport, and how waves interact.
It really is quite something. Understanding these fundamental rules lets you analyze everything from, musical instruments and radio waves to earthquake detection and the expansion of the universe. Hopefully, you now feel equipped with the language and concepts to see waves everywhere.
Absolutely. And maybe here's something to chew on, a final thought. We talked about a shock wave being this cone of high pressure from supersonic travel, heard as a sonic boom. What happens energetically and physically if the source goes much, much faster? Say 5 times the speed of sound, or 10 times hypersonic speeds. How does that incredibly compressed, rapidly moving pressure front interact with things it passes through? Think beyond just the sound. What physical effects might that extreme, sudden pressure change have?